All right, let's get started. Yeah, happy Sunday, Mitchell, and also everyone. Thanks for making this special effort, right, to attend this makeup lecture. Today, we are going to be talking about caches. Right? We're going to talk more about caches. You know, everyone can use more cache, right? Hopefully, you guys like the title today. I'm gonna just cut to the chase. I'm not gonna make any announcements. I'll talk a little bit more about Prim 2, maybe on Tuesday, when we have a larger audience. Today, like I said, I'll just cut to the chase and talk about the technical content right away. One quick thing, so before we come back to cache, so let me just quickly introduce this hexadecimal format. I think this is something that most of you are probably already familiar with, but this is going to be used in homework 7. I think it's already used in one of the or a few of the labs already, right? But let me just formally, officially introduce a hex format. With this hexadecimal notation, really, we are talking about this base 16 system, right? And we have been looking at decimal, right, which is base 10, and then binary, right, base 2. But in many cases, we actually prefer to use this base 16 or hex system just for the sake of convenience, right? In this case, right, since the base 16, for each digit, right, each hex digit, we can represent 4 bits, meaning that we can represent 16 numbers. If you look at the mapping, right, so here's the mapping between the, I'm not sure if I can see my, somehow my highlighter is not showing up on the screen, which is fine. Hopefully you can still see my mouse, right? So, over here, we are seeing this, showing the mapping between the hex, binary, and decimal, right? From 0 to 9, right? Up to this point, the hex number is no different from the decimal number, right? But if you look at this range, from 10 to 15, we are using A, B, C, D, E, F, right? We are using this a capital, right? The uppercase, right? As simple as this. All right, so let's just do a quick practice, right? Again, this is useful for us to compress the binary string in many cases. So it's so this binary string is more readable for human being. Usually divide it, right? So the binary string, we want to convert it into hex number. We chop it into these 4-bit segments, right? And then we read from the LSB, right? This given bit from the right to the left. First one is simple, right? That's just a 7. Second segment, what is that? Can you just quickly convert it into a hex digit? 13, right? In decimal is 13, very good, which is a D. Right? Next is just 4, right? That's something that we already familiar. Next one is also easy to read. At O1s, right? O1s means 15, which is F. Yep, this is a special hex digit. Next, this is just 8, right? And how about this one, 1010? This is a 10, right? Which translates to A, very good, right? Last segment, just 3. All right, okay, so that's how we do the translation. This is very straightforward, but one thing I want to note, I already mentioned this, right? So really, with hex, there's a hex digits, right? So we are not, using this as a new kind of a data representation in our hardware. That's not the case. Our hardware only understands binary numbers. Instead, we are using this hexadecimal numbers really as a more compact way to write binary strings, binary numbers. That's it. Okay. This is the use case, right? And in homework 7, I think there's a problem where I ask you guys to look at a sequence of memory addresses using the hex numbers. That's where you actually need to convert the hex into the binary string first before you proceed. Okay, any questions about hex? All right, if not, let's come back to cache, right? So last time we talked about DM. What is DM again? DM cache, that's a shorthand for a certain type of cache, right? Direct map, very good, Katie. we talk about how to break down the memory address, right? Given the rec map cache, given certain cache configuration, right? We usually look at how many blocks we have, right? How many bytes per block, right? We can break the memory address down to a set of fields, right? We have tag, index, and offset. Okay. Today, I'm not gonna force a quiz, right? Since we only have a very smaller class today. But I still want you guys to do a quick exercise, right? To do a quick practice question on item pool. Can you guys go to this link? Same link again, so that I can force you guys to refresh your memory about how we break down the memory address for direct map cache. And this is very important. Okay? By important, you guys know what I mean, right? Right. Okay, so the link is enabled. Right, please go there and enter your answer. We have a direct map cache. This is a full 16-bit memory address. We have two configurations. For the first configuration, we have a 16-block cache, where we have this 4 byte per block. That's a block size. Okay, you guys are supposed to tell me how many bits do we have for byte offset, how many bits for index, and how many bits for tag. And same thing for the second configuration. All right, we'll move on in a minute. All right, I think many of you are still working on the problem, right? But that's fine. But I'm going to talk about this in 20 seconds or so. All right. Okay, so let's take a look at this this problem, right? First, we have 16 bits, right? So this is the full memory address. Later, you guys really need to distinguish a full memory address, right, from a memory block address. I'm going to emphasize that again in this lecture also. With this one, we have, let's look at A, right? We have 4 bytes per block, right? Which means how many bits for the byte offset? 2, right? 2 byte offset bit. Very good. Index, what's the use of the index? Index bits are used to address the cache blocks, right? We have 16 cache blocks. So how many bits do we need for the index? 4. Excellent. Then the rest will be tag, right? That's basically 16 minus 4 minus 2, right? Which is 10 bits. Okay, so this is the first cache configuration. Second one, right? B. This is where I increase the, this block size. With this one, we have 8 bytes per block. So read the byte offset bits, right? We have 3 bits here. Okay. And this is actually the size. The size of the total size of the cache remains the same, right? We have more bytes per block, but we have fewer blocks now. How many bits do we have for index? 3, right? And how about tag? Same thing, right? 10. Okay. Any questions? So it's really important for you guys to to know this and be familiar with this, right? It's an addressing scheme, and we're going to practice and practice, right, until you guys are really comfortable with this. We're going to be doing something like this for another kind of cache as well. All right, so this is direct map cache, and these are the answers, right? I'm going to check your solution against this. These are the solutions. Okay. We talk about these are two kind of configurations. Right? Also, last time we looked at two kind of direct map configuration. One has a 4-byte block, right? The other one has an 8-byte block. You may wonder, right, what are the trade-offs? Right? In general, if you use a larger cache block, right, these may reduce the miss rate, right? Because indeed we have we can exploit this spatial locality, right? But with the but there's this a trade-off, right? Because if you have larger blocks, that means if you fix the size of the cache, the total size of the cache, we have fewer blocks in the cache, right? That means we may have more complex. So that's a downside. That may actually increase the miss rates, right? We really want the miss rate to be as low as possible for this cache to work. And also the larger block may also incur a longer delay, right, when we move the data between the memory system and the cache, right? Because we are transferring one block at a time, right? Not one byte or not one word. That's how we make the transfer. Okay, so basically this is a trade-off, right? This is something that we have to, in practice, we have to do a lot of empirical study to really figure out what is the best cache configuration for the given application or the given set of benchmarks. Okay, so this is direct map cache, right? Hopefully you guys are already familiar with the addressing scheme. If you understand that one, you understand the direct map cache pretty well. But let's come back to this intuition again. Okay, this is the one picture that I showed you guys on Tuesday. So where we look at the sky, right? We all agree that. So in this case, right, on this picture, the backpack is the main memory, right? The pockets, they are the cache, right? And we put cell phone right in our pocket in most cases, right? So that's the most frequently used item. And we also add some spice, right, to this analogy. And we assume that, right? So this guy is actually a special agent, right? Who actually owns a lot of cell phones, lots of smartphones, right, for different missions. And we actually use this analogy, right, to talk about we also give an analogy, right, in this context, right, for the direct map cache. So where I think we talk about, right, this guy owning at least 4 brands of smartphones, right? Apple phones, right, is an older model, right? A newer model, and BlackBerry, right? Older, newer Google phone, right? And Samsung, maybe, right? Okay, so these are the memory blocks, right? That he has, right, in his backpack. And we have the cache blocks, right, which are the pockets. So let's say, we have 2 in the front, right? And this is basically the 2 pockets and 2 in the back, right? So we have 4 pockets. For direct map cache to work, so one scheme is we basically do this kind of mapping, right? Okay, these 2 phones, right? These 2 type of phones goes to P0, pocket 0, and these 2 kinds of phones, right? They're always mapped to pocket 1, right? Similarly, we can do something similar, right, for Google phone and Samsung, right? Okay, this is basically a direct map cache, right? Okay, but there's a downside, right? So let's say this guy, for a certain mission, right? This guy wanna use, right? So what if, right? So let's talk about the what if scenario. What if, right, this guy wanna use A0, right, B0, right? Basically Apple phone and this BlackBerry phone at the same time, right? Very often. Same thing for A1, B1. So then this kind of mapping is not that convenient, right? It's pretty low performance. So if this guy has to use A0 and B0 quite often at the same time, that means that this guy has to constantly swap, right? Has to constantly replace A0, right, by B0, because these two, right, these two blocks or these two phones are mapped to the same pocket, right? And we assume that each pocket can only hold one phone. That means this guy has to constantly juggle, right, between these two, a constant switch, so which is pretty inconvenient, right? So this is actually something later on we're going to see. It is something called a conflict miss, right? So basically, there will be a lot of misses in this cache system. What do we do? How can we make it more flexible so that we can reduce the number of misses? Any ideas? Hopefully this analogy still makes sense, right? How can we increase the flexibility in our cache system, right? In this case, what do we do? Any suggestions? Right. Basically, you know, we with Emily, right, we map A and B to P2 and P3, right? So that's one idea. But if we want to limit ourselves to the front pockets, right? Let's say P0 and P1 as the front pockets. So maybe just treat, right, these two as one set. Okay. I'm going to introduce this notion more formally. Treat it as one set. So in this set, okay, this A0 and B0 can go to either pocket 0 or pocket 1. Right? That helps a lot, right? So that means these two phones can coexist in the pockets, in two pockets at the same time. That helps a lot, right? In terms of reducing the misses. What's the downside here? There is a downside, right? There's a trade-off. There's really no free lunch. Really, in computer system, I keep mentioning this. Right? Everything's a trade-off. There's no free lunch. In this case, for this guy to check whether he has a right phone or not, he actually now need to reach into both pockets, right? And then check both phones and check the tag, check the brand. But at least there is some additional flexibility, right, with this mapping. Does it make sense? Okay. Any questions about this analogy? If not, you pretty much understand, right? This new kind of cache. But let me try to make it more clear, right? In the cache, right, settings. So over here, let's talk about the direct map cache again. Right, this is the block placement. Right, we have 8 blocks, right, in the main memory. We have 4 blocks in the cache, right? If you look at direct map cache, so the same, right, the memory blocks with the same color are mapped to the, right, to one of the cache block, right? In this case, the blue blocks, right, are mapped to the blue memory block, are mapped to the blue cache block, yellow memory blocks are mapped to the yellow, right, cache block, etc. But over here, so there's not much of flexibility, right? For any given memory block can be only mapped to one of exactly one of the cache block. All right, how can we make it more flexible? You know, if we treat this thing, right, so we call this P0, coming back to our analogy, right, so this is the 2 pockets, right? One is the P0, the other P1. We said, how about we form a set? What do I mean by that? How about we just call, you know, there's two of the form group one of the 2 of these cache blocks, right? And form them to be a set. In this set, okay, they are indistinguishable. What do I mean by that? So first, yeah, we still have 4 cache block, right? But now we have 2 sets, right? 2 sets. And per set, within each set, we have 2 ways, way 0 and way 1. Each way corresponds to a cache block. All right, so this is the setup, right? This is the configuration. And now, so the mapping scheme is different with this so-called set-associative cache. So now this cache is, we have a new name for this kind of cache. It's called set-associative cache. In this specific case, we have a two-way set-associative cache since we have 2 blocks per set. In this setting, okay, with the set-associative cache, we are mapping the memory blocks to a set, not to a specific cache block, but we are mapping the memory block to a specific cache set. And each cache set contains multiple blocks, right? And within the same set, within the set, so if you look at block 0, right, the memory block 0, 2, 4, now we can put block 0 here. Okay, we can put block 4 here. Okay, it doesn't matter. Oh, block 4 can go here. Okay, and 0 can go here. When we actually move data from in memory to cache. So that's why I'm saying that within the set, within the same set, these cache blocks are indistinguishable. This gives us some extra flexibility, right? But of course, you know, over here in this case, in this configuration, so we have to search 2 ways at the same time, right? When we want to find a match, we need to compare tags, we need to check developers, we need to search both ways at the same time. Is it clear? So how this roughly works? Of course, I'm going to give you guys more concrete examples. Right? But the key idea here is that we are mapping the memory blocks into the cache set, right? Which is a group of a collection of cache blocks. All right. So if this is somewhat clear, right, at a high level, let's try to be more specific, more concrete. So over here, I'm using the decimal numbers, right, to indicate the address of the memory block. This is the memory block address, which converted into the binary numbers, right? That just this first one 0, 0, 0, 0, 0, 1, etc. Right? 1, 1, 1. All right. Oh, there's a question. Emily's asking map some of. Oh, no, this is not the one. Latest question. I think it's fine, right? This is the old question. All right. So coming back to the set-associative cache, what I'm trying to ask is, in this case, how many index bits do we want? Do we need? Right. In the previous case, if we go back to this one, right? We have 4 cache blocks, right? This is a direct map cache. We need 2 index bits. We are mapping to the cache blocks. But in the new setting, with a set-associative cache, we are mapping to sets. Okay, excellent, right? We just need 1 bit. Okay. See here, if you look at the yellow blocks, right? The yellow memory blocks. Let me write down the binary string for binary address for a few more blocks. Okay. Just look at the last bit, right? For this yellow blocks, this is 110. They are all 0. We just need to extract the last bit in this case, right, from the memory block address, and use that bit to index the corresponding cache set. Right? For the yellow one, we just need to, if it's a 0, right, index with 0, then we index cache set 0. Otherwise, if the index bit is 1, right, 0, 1, we, for the blue ones, right, we index cache set 1. That's how it works. Right. This is the key intuition, right? We are trying to map to the set. More formally, right? So this is the definition with k-way set-associative cache. We use the index bits to determine which set to address, and each set contains k ways or k blocks. And all these blocks, all these ways are searched in parallel. Basically, we need more, right? We need more hardware resources we need more comparators. We need more to check the comparison, to compare the the tag, also to check the valid bit. Right? And there's an extreme case. Actually, we can come up with something called fully associative cache. This is an extreme case. This is where basically we only have one set. We have one big set, which contains all the cache block in the cache. So that's where we don't really need any index bits. So basically any memory block can be mapped into any cache location. Right? So this is where we have the extreme flexibility. But of course, there's a price, right? That's where we have to search all the entries at the same time, which is pretty expensive in hardware, right? So that's usually that's actually the reason. Usually for fully associative cache, we can only afford to have a relatively small cache. Otherwise, we have to use something with less flexibility. Okay, this is the definition. Let me show you the address breakdown again. Over here, we also have this full memory address. Right? We do need to care about even the full memory address. We do need to care about the cache. We do need to care about the byte offset bits, right? So we use the LSB, right? The last few bits to indicate how large is the cache block or memory block. Then we have the index bits, right? So this one address the cache sets. The remaining bits are the tag. This is very similar to direct map cache, right? Okay. Actually, direct map cache is also a special case of set-associative cache. Make sense, right? Why is that? How many ways do we have for direct map cache? Why is it a special case of a set-associative cache? How many ways do we have in the DM cache or direct map cache? Just one way, right? Very good, Katie, right? Just one way with direct map cache. All right, so with this breakdown, right, we can again try to analyze the size of the cache. Right? So this is the size of the block, right? Depending on how many bits we have for the byte offsets, we can decide how large is the cache block. Then given the index bits, we can determine, right, how many sets do we have, right? 2 to the I is the number of sets we have. Then given the number of ways, we can determine, right, how many blocks do we have in total in the cache. Right? Basically K times the number of sets. And we have right, so given all of this information, we can determine how large is the total size of the cache. Okay, I'm not gonna spend too much time on this, right? It's actually very straightforward, but make sure that you guys verify the maths here. All right, so let's look at the concrete example. In this case, we have a 4-way set-associative cache. Hopefully you guys can see this full memory address, the breakdown. Over here, we have 32 bits, right? So this is a full memory address. And we have 4 ways, right? We have 8 bits for index. What does this mean? How many sets do we have? We have 8 bits for indexing the cache sets. How many sets do we have? One thing to analyze, right? So later on, when you guys analyze this kind of set-associative cache, it's extremely important to understand. First, figure out how many sets do we have. That's the first thing you want to figure out. Okay. 2 to the 8, which is 256. Right? See here, it's basically 256. We have 256 sets, and this is a 4-way. We have 4 ways, right? See here. This is basically way 1, right? Way 0 or way 1, 2, 3. Right? 0, 1, 2, 3. We have 4 ways per set. So how many cache blocks do we have in total? 4 times 256, which is 1024. Right? Very good. Again, 256 sets and 1024 blocks in total. Any questions so far? right? It's actually very similar, right, to direct map cache. The main difference is that now we have more than one block, right, per set. That's it. And we search all these blocks, right? We search all these ways. We search all of them, all these 4 ways all together. And each way has a data block, right, has a tag, has a valid bit, right? And we search all of them in parallel. And we make comparison, right? This is where we need to allocate more comparator, more AND gate, right, per way. And eventually we merge the result, right? And that's where we select the data. If we have, in the end, we have an OR gate, right? If we have a hit in one of these ways, right? In one of the entries, then we have a hit. Using that information, we actually over here we are using a one hot mux for the mux select, and we use that information to select the data. Okay, any questions about how this one works? The key thing is, I have to emphasize again, right? The key thing is we are addressing the cache set and we are searching all the ways in the set. We hit one set at a time and we search all the ways in the set at the same time. Amanda's asking, is the offset the number of things in the set? This is a good question. Not quite. This is the, oh here, this is the byte offset, right? Byte offset. This one still indicates we use the byte offset information to determine how large is the data block, right? So in this case, it's going to be 4 bytes per block. How many ways do we have? That's actually determined. So this one you cannot directly tell from the memory address breakdown, not anymore. This is given. So you have to tell me. So later on, I will tell you how many ways do we have in the cache. So based on that information, you can determine, right, how large is the total, right? What is the total size of the cache? Does that answer your question, Amanda? Again, the byte offset is only useful for determining the cache block size. And how many ways do you have is a separate information. Okay. All right. Okay, so let's talk about the concrete example. Here's a simple case. We have a 2-way set-associative cache. And per block, we have 4 bytes. And the cache holds 4 blocks. We have 2-way. It's a 2-way set-associative cache. Okay, what does this mean? First, how many sets do we have? That's the first thing, right? I keep saying that for this kind of cache, set-associative cache, first thing you guys want to determine is how many sets do we have? We have 4 blocks, 2 ways. How many sets? You know, it's already in the slide, right? You already see the picture, but right, I just want to make sure that you guys do the calculation on your own. Right? We have 2 sets, right? We have 2 ways, 4 blocks, right? Then 4 over 2, we have 2 sets. Right? 2 sets. Per set, we have 2 blocks, right? That's why we call it 2-way cache, 2-way associative cache. All right, given this information, first we can clearly tell how many bits we have, right? For the byte offsets, that's just 2 bits, right? Since it's 4 bytes per block. All right, how many index bits do we need in this case? It's a 6-bit memory address, right? Just one, since we have 2 sets. The ID, we index the cache set, right? Just 1 bit. And the rest is the tag. Okay. Right. And also tag plus index, right? So these form the memory block address. All right. Again, one more time, right? So we have 2 sets, right? Per sets, we have 2 ways. And this is the abstract diagram of the cache. Right? And we use this one, right? So we have some indices here. 0 means set 0, 1 means set 1. Each row means a set. And per row, we have 2 ways. Okay, same address string. So you guys have already seen this address string, I believe, in the last lecture. But now we are trying to map this into a different kind of cache. So we have this set associative cache now. Okay, same assumption. Right? We have this registers, right? RF, right? Which is holding 4-byte value. On the right, I'm only showing you the memory block address. This is not a full 6-bit address. And we have data, right, stored in the memory, and we're using decimal number in this case. All right, so let's look at the first line, right? This one, first read. Initially, the cache is like basically invalidated. All the cache lines, all the cache blocks have 0 value bit. Okay, that means there's really nothing useful in the cache. So of course, the first read is going to be a miss, right? It's going to be a miss. Okay, and we use the index bits, right? The blue one over here, the blue bit to address the cache set. So in this case, we are addressing the first row or the first set, and this is a miss. Right? That's where we read from the main memory, right? We load the memory block, and then put it into the cache. So see here, we have 2 ways, right? That doesn't really matter which way, right? We put the cache block in, because these 2 are indistinguishable. They are the same. Let's say we just put this 100, right? So this value, this data block, into the way 0, or the left way or left entry, and we update the tag and also update the value bit, right? Okay, so this is the first read. Second one, if you look at the second one, if you move on over here, do we have a hit or miss? R2, if we read to R2, hit or miss? Miss, right? Because we haven't seen this address yet. We haven't seen the memory block address yet. It's a new address. Obviously, it's going to be a miss, right? Which set do we address? Which row do we address? Cache row or cache set? 0, 1. 1, very good. We read the blue bit, right? Again, this is a miss, right? In this case, we put the data. We allocate the cache block, right, in one of the ways, and then put 110 over there, right? Okay, so next read. This one is also a new address, right? And this is also a miss. But in this case, this is actually interesting. This is unlike the direct map cache case. So in this case, we don't need to evict this block, right? We don't have to kick this guy out, not anymore, because we have another way available. We have another entry available over here, right? This way is available. That's where, instead of kicking out 100, right, this block, we will just use the other way, the other empty way. That's where this extra flexibility is really useful. Make sense? It is also miss. We load 140 over here. Right? So just in case you guys forget about why we load 140, right? This is where we check the memory block address, right? And this is the memory block address, right? The color bits, the tag bits plus the index bit. These bits form the memory block address. We read from the corresponding memory block address, which is 0100, and that's why we load 140. Okay. All right. Next one. Is it a miss or hit? You want to read R2 again? Read into R2 again, not read R2. You actually write R2. It's also a miss, right? Because this is also a brand new address. It's a brand new memory block address. Right? So the next one is also a miss, and we put the corresponding data block, right, the memory block, into the cache set 1. There's an empty way, right, which we can use. We put 170 there. All right. Okay, so the next read, right? The next line is going to be more interesting. Do we have the miss or hit? Have we seen this memory block address before? Yes, right? 00, 0, 0. So we have seen this before, and it matches this block. Right? Okay, so we do have a hit. Okay. And we just directly read from the cache. We don't need to access the main memory in this case. All right. Any questions? If not, last line, hit or miss. This one. Right. Also a hit. Right. This is where we look at the second set or cache set 1, and we have a match. Right. We have a match here. The tag bits, right? We just compare the tag bits. 0, 0, 0, 0, 0 here, and the value bit this one, which is a match, which is a hit. Okay, right. So with this increased flexibility, if you guys remember, right, in the Tuesday lecture, I think we only got 1 hit, right? In this case, we have 2 hits, which is an improvement. Right? All right.